Hey guys, welcome back to my YouTube channel. This is Dr. Anjit. So I'm going to talk about a series of videos about the 11th edition of Robbins, which has been updated. So there's a new topic which is there in the 11th edition of Robbins, which is termed as integrated stress response. The first question is, what is it and why is it required? Let's say if you have read about Robbins or previously about the cellular adaptation injury, we always said that whenever there's a stimuli, so automatically the stimulus has multiple effects on any cell, right? The stimuli can actually help in the cellular adaptation, and cellular adaptation could be hyperplasia, hypertrophy, metaplasia, atrophy, or it can also cause a cell injury or a cell death, right? So one of the important things in cellular adaptation is to kind of reduce the stress on the cell and to make it survive during the stressful stimulus, right? So, what the integrated stress response primarily says is we have understood or we have unlocked what and how exactly a cell escapes during the stressful stimuli. So, we have categorized stressful stimuli into four various categories, and for each of them, we have got kind of an downstream effects with respect of few receptors and few downstream pathways and kinases involved. But what primarily we're trying to say is this integrated response or the response of a cell to any stress is going to primarily culminate on phosphorylation of one important factor, which is EIF2 alpha, which is nothing but an eukaryotic initiating factor 2 alpha. So, because of this phosphorylation, the ultimate goal, what the cell does is it globally inhibits, okay? It globally inhibits the protein translation. So, ultimate goal is okay, I'm struggling now, so let me kind of put my entire cell into a kind of an hibernation mode. So, once the stimulus is gone, I'll definitely regain the confidence and come and become more functional as usual, right? So, this is the ultimate goal of the integrated stress response. So how am I going to do that, right? There's a new image in Robbins. If we carefully look at this, whenever there's an endoplasmic reticulum, ER stress is endoplasmic reticulum stress. So this is automatically increased by the number of misfolded proteins. So in an older cell or anything or any disease, when there's a number of more misfolded proteins, it puts this as on endoplasmic reticulum. And the endoplasmic reticulum kind of activates a downstream pathway called as PERK. PERK is nothing but PKR, protein kinase like ER kinase, right? So that's PERK, protein kinase like ER kinase. That's all. Endoplasmic reticulum, it's a kinase. All these are kinases, right? So that kinase, it phosphorylates. If you can see, it's happening entirely in the rough endoplasmic reticulum, right? Ultimately, it's going to phosphorylate the eukaryotic initiating factor. That's the final thing what we already discussed, right? So, agar if there is a problem in the amino acid starvation, so I'm going to have protein deficiency, right? So what happens is whenever there's a less protein response or less amino acid in the person, it's like a starvation. That also says that my cell is struggling. Let me put a halt on the protein production mechanism of the cell. That's global inhibition of protein translation, so that I can survive for a bit a longer period, right? That's all, right? If you have a viral infection, on the other hand, I'm going to activate simple protein kinase R. PKR stands for simple protein kinase R. Okay, so that will kind of put the entire cell's machinery into slowdown or like in a hibernation mode, right? If there is an iron deficiency, right? Because when iron is not there properly in adequate amounts, my bone marrow has to kind of adapt to it, right? So in case of an iron deficiency, a heme deficiency sensor is there on the erythroid cells, that is HR1, right? So this is a heme deficiencies sensor. It can identify the amount of heme there. It's a heme deficiency sensor, and it kind of says that okay, iron is not there. Probably I'll not be able to have proper heme. Let's not produce hemoglobin now. Let's kind of keep it down, right? So what is the goal? The final goal is adaptation. How do I adapt? So these not just suppress global translation, that's the primary effect though, it also induces antioxidant pathways. It also helps in the survival of homeostasis by suppression of global translation, and also not just that, it also increases antioxidant pathways. Okay, so once antioxidant pathways are increased, obviously my cell will have more energy to fight against whatever is coming up, right? Also kind of upregulates, it's kind of a link what you're trying to do. It also upregulates autophagy genes. So this is the primary mechanism what my body does. Okay, again it fails, automatically I'm going to go and trigger autophagy genes and maybe consume all the protein and still try to conserve the cell and prevent the cell from cell death, right? Understood? It also increases the fourth one. It also increases few chaperones. Chaperones are something which helps the binding to the unfolded protein and helps in the protein recycling mechanism bioubiquitin potassium pathway, right? So primarily goal is whatever may be the initiating factor, I'm trying to kind of counteract that and make my cells survive for long. Amazing process. So why does it, how is the clinical relevance here? So why did we read about integrated stress response? The first thing, let's take from the easier one. The first thing is, let's take viruses. So virus, what primarily does is, once virus comes into the body, right? Like few of the proteins we saw, virus kind of activates your protein kinase R, right? And kind of inhibits the eukaryotic protein translation. So by manipulating ISR or an integrated stress response, the virus will actually favor viral protein replication. So till now, we were in the dark, not knowing how exactly the virus is able to increase its protein production. Because my cell primary goal is to help my body's protein. How it's able to increase viral protein replication? As simple by manipulating ISR. As simple as that. Second, the most important thing is the cancer tumor cells. Automatically, everything is going to stress upon cancer, right? Tumor cells uses these mechanisms to adapt during a very difficult condition like a tumor hypoxia or a nutrient stress, because cancer grows very fast. It'll take my body good amount of time to adapt to the increased replication, right? So tumor adapts to the nutrient stress or an hypoxic condition by using these mechanisms, by using primarily using ISR. Now the goal is I have to tweak ISR. Our goal is always only one thing. How do I use it kind of to make sure that the patient's outcome is being managed better? So let's say this is an adaptive response, right? Adaptive response by default, you all know that there's some point of time all these adaptive response is bound to fail. So if the adaptive response fails by ER stress or PERK or by viral or PKR response, what actually does is it activates a pro-apoptotic factor called as CHOP. Do remember there's a new pro-apoptotic guy in the ground, that's CHOP gene, right? Apart from all the backs back and everything, it's going to activate the pro-apoptotic factor. This will create apoptosis. Okay, this is the outcome if this process fails, right? So if you are preparing for an INICT, this might come into the perspective. Please have a look at them. And this is something which is new in the 11th edition of Robots. Follow me for more, and let's read chapter by chapter what are the changes, what are the relevant changes with respect to the knowledge acquisition, and also maybe what might come in the exam point of view. If you follow me on Instagram, I'll send you the notes of this as well so that you can read it whenever possible, right? Thank you for your time. Bye bye.